Welcome back. In this lecture, we will start discussing elements of thermodynamics of electrochemical system. This is the first part of many lectures. In this lecture, we will interpret the electrochemical potentials that are reported in electrochemical tables and certain aspects of measurement that goes with what is being tabulated with respect to electrochemical potentials. In the last lecture, we addressed certain aspects of electrostatics. This is going to be useful in interpreting many quantities in electrochemical systems. Two important quantities of electrostatics that you should get a good feel for is the electric field and the electrostatic potential. These are mechanical potentials. There is no dependence on temperature. You should be able to understand the symmetry of two systems. One is a system that has spherical symmetry because, for example, if you have an ion, the electrostatic field around an ion will have spherical symmetry. And also the symmetry that you see in a parallel plate capacitor. That is also of relevance to electrochemical system. And for both these systems, you should be able to plot the electrostatic field and compute the electrostatic potential, understand the meaning of conservative fields, and so on. We also looked at the simplest electrostatic system of relevance to electrochemistry. One is, let's say you have a parallel plate capacitor. So these two plates are made up of metal. So for a metal, it has infinite mobile charges. So the charges can be present only at the surface. Corresponding to the surface charges, there can be a jump in potential. And when you plot the potential drop, that is in this manner. If you consider an ohmic conductor that you typically see in your electrostatic classes, you have only one kind of mobile charges. So if you are thinking about transport of current, you need to consider only one kind of mobile charge. As opposed to all these things, in an electrochemical system, there are certain differences. The first difference is that if you have an electrolyte, the electrolyte has both cations as well as anions. So there can be two kinds of charge carriers in the electrolyte. So that is represented, for example, in this system. If you're considering an electrochemical system, for example, this can be a cross-section across an electrolyte. There can be two kinds of charge carriers, cations and anions. Both can carry current. In addition to that, the nature of the double layer is fairly complex. Here it had a simple charge distribution in the double layer, but here the nature of charge distribution can be fairly complex. We'll address this in the next few lectures, but all we need to understand is that it's not as simple as what you see in electrostatic condition. And we also looked at the contrasting behavior of insulators, electronic conductors, and ionic conductors. So supposing you have an insulator between these two charge plates, and when you impose a potential, what we are plotting here is Q versus time. Because you impose a potential, just at that moment, there is be a finite current, and that finite current would have accumulated charge in the metal plates. That's what happens when you have an insulator between these two metal plates. And the charge accumulated is given by certain equations that are from your classical electrostatic literature. As opposed to this, if you have, let's say, a potential applied across an electronic conductor, the potential applied will give rise to constant potential applied will give rise to constant current. Therefore, the charge that is being transferred across a particular cross section will increase linearly with time. As opposed to these two situations, in an ionic conductor, what happens is that the current that is transferred across a cross section exponentially decays in an exponential manner. So let's understand this behavior qualitatively, and we will describe this more mathematically in a quantitative sense in a later lecture. So what happens is that when you impose a potential, imposition of potential is associated with charge accumulation in the metal plates. In response to this charge accumulation, there is ion movements. The positive ions move in the opposite direction to the negative ions and accumulate at the interface. So the negative ions will accumulate near the positively charged plate and the other way around for the positive ions. The driving force for this movement is highest as soon as you impose a potential. Therefore, the current that is flowing across the cross section is highest at t equal to 0 or small t's. As t increases, the driving force for charge accumulation and hence the current flow becomes lesser and lesser. Therefore, the current decays in an exponential manner, and the charge accumulates in this manner. So these are three contrasting behavior of insulated, electronic conductor, and ionic conductor. Even though there are contrasting behaviors, certain other relationship is still valid inside an electrolyte. For example, the relationship between current and potential drop connected via a conductivity is still valid. We'll describe these things quantitatively as we progress in this series of lectures. Moving on. Okay, so the last thing which we saw in the previous lecture was that the first quantitative description of an electrochemical reaction given by the Faraday's second law. Even though this is a bookkeeping, just an accounting principle, doesn't involve any thermodynamics or kinetics or transport of electrochemical systems. Why is it important is this was the first quantitative relationship that was utilized for describing an electrochemical system. This was done by Faraday in 1800s. So you have to appreciate the time when it was all done. Okay, the nature of ions, nature of electrons was not at all clear, but Faraday managed to come up with a quantitative relationship and prove that from empirical explorations he conducted on electrochemical systems. Moving on, the central theme of this lecture is how do you think about cell potentials? Supposing you have an electrochemical system, the following electrochemical system, how do you measure the cell potentials and what do they represent? How do you express them in terms of principles of chemical thermodynamics? So what is the system we have here? This is the Daniell cell. So on one side, you have an electropositive metal. That means this metal, zinc, would tend to get oxidized. It increases its oxidation number to 2. On the other side, you have a less electropositive metal, copper. That means copper will always want to be in the 0 oxidation state compared to zinc, right? So copper 2+ will get reduced. When you connect such a system, there will be a voltage difference. We want to understand the meaning of this voltage difference. Okay, that's what we mean by cell potential. All the time, we don't draw such a schematic. There is a more succinct way of representing the system. This is the electrochemical convention that is used for representing this system. A single line indicates a phase boundary. In this case, the phase boundary is between a solid zinc rod and an aqueous system. Similar phase boundary exists in this side also. And there is a semi-permeable membrane which allows only sulfate ions and rejects zinc 2+ and copper 2+. The semi-permeable membrane serves two roles. The first role is even when there is an electron flow, the charge neutrality is maintained by the semi-permeable membrane because it allows sulfate ions to translocate across the membrane. That is the first role, to maintain charge neutrality in both the chambers. The second role of the semi-permeable membrane is to maintain separation between these two chambers. The electrochemical environment in this chamber is different from the electrochemical environment in this chamber. That difference in electrochemical environment is responsible for the generation of cell potential, and semi-permeable membrane plays an important role in this for establishing this separation. There is a convention which is utilized in electrochemistry. U is a positive quantity, so we typically represent the cell potential as the electrode potential of the right electrode minus the electrode potential of the left electrode. On the right, typically there's a cathodic reaction. That means Cu2 plus is getting reduced to copper. The oxidation number decreases with the addition of 2 electrons. On the right side, there is a cathodic reaction. On the left side, there is an anodic reaction. Because of such a representation, when you go and look up the electrochemical potentials for these reactions, you would see that this is a more positive quantity. Eventually, we'll get the cell potential to be a positive quantity. So this might even be a negative quantity. The negative of a negative number will be a positive quantity. Overall, the cell potential will be a positive quantity. We'll look at the electrochemical tables in the next few slides. So this convention, you might have also heard in your high school. So it might have also been mentioned that the cell potential is represented as EC minus EA, E cathode minus E anode, right? So we'll always get a positive number in that case also. Moving on, so we want to relate the cell potential to some aspects of electrostatics. So the electrical work in electrostatics is defined as the charge that is transferred across a potential, right? So here we are going to use that kind of notion to define electrical work. However, this potential which we are referring to in an electrochemical system is a thermodynamic potential. It's a potential that depends upon temperature, pressure. Okay, the electrostatic potential is a mechanical potential. So the work involved in an electrochemical system is thermodynamic work. It depends upon temperature, pressure, and relevant mole fractions of the relevant chemical species. But by analogy, we can think through this electrical work in an electrochemical system. And we know from chemical thermodynamics that to get work out of a system, we need a decrease in free energy. The decrease in free energy can be related to the work that can be obtained from a system. Here we are describing a Galvani system, that is electrochemical system from where electrical power can be taken out of the system. Okay, the opposite is an electrolytic system. So in a Galvani cell, you undertake an exothermic reaction. Delta G is negative. The overall reaction is exothermic. So what is the overall reaction? The overall reaction is Cu2 plus zinc gives Zn plus Zn2 plus Cu. That's the overall reaction, right? So copper gets reduced, Cu2 plus gets reduced to copper 0, and Zn gets oxidized to Zn2 plus. That overall reaction is exothermic, and because of delta G associated with that exothermic reaction, you can get electrical work out of the system. Putting these two together, we have this very important relationship connecting the free energy change involved in the electrochemical reaction to the overall cell potential. Again, all these things you might have seen in your high school itself, but we are just revisiting and trying to look at this more deeply. You can express the delta G using delta G naught. This is the delta G naught under standard condition, and this is the activity of the relevant chemical species. So this is delta G at any non-standard condition, any temperature, pressure, and chemical composition. You can relate delta G to delta G naught and activities in the following manner. Putting this and this equation together, we have the representation, the fundamental representation of a Nernst potential, Nernst equation, right? So this Nernst equation has to be utilized under equilibrium condition. So equilibrium conditions exist when there is no current flow. Voltmeter is a high impedance device. Therefore, there is negligible current flow. There has to be some electron transfer to measure a potential difference, but current flow is negligible. So this cell is still at equilibrium. You can represent the cell potential using the Nernst equation. So again, this is something that you might have seen in your high school, except that instead of activity, you might have used concentration. Okay. All right. So two things I'm emphasizing here. First, we emphasize certain electrochemical conventions, and then we are connecting the electrochemical cell potential to chemical thermodynamics. We'll go further into this. The issue here is we are often concerned with the cell potential measurements between pairs of electrodes. So these pairs of electrode, if you go and look at the electrochemical tables, every electrochemical system, by electrochemical system, I mean a system wherein there is electron transfer involved, okay? So if you want to measure pairs of electrode, the philosophy we will implement is that we are going to calibrate each of this electrode. Okay, there are two electrodes here. Each of this electrode, if it is calibrated against some reference system, using such a calibration, we can discuss any pairs of electrodes. That is the philosophy we are going to take. So what is involved is measurement of a working electrode potential against a reference electrode. So what is a working electrode? Here there are two working electrodes. So working electrode is where there is action. Okay, that's what you're interested in when you're doing the experiment. And you are trying to understand that. That is called the working electrode. Again, just jargon. Working electrode is where the electrode of interest is the working electrode. Here we are represented as a test electrode. So what is the philosophy? We are going to calibrate the relevant electrochemical properties of the test electrode, which will be used as a working electrode, against some standard system. Okay. What is the standard system? You will see that the standard system is capable of providing you with a reference level, reference energy level of electrons. Okay, so this standard electrode is called the standard hydrogen electrode. We will see what it entails. The standard hydrogen electrode entails three components. There is a platinum electrode, which is dipped in an electrolyte, which is acidic in nature, and hydrogen gas is bubbled through that system. When you do that, what we are to notice is that an electrochemical equilibrium is established. Platinum is a very good electrocatalyst for this reaction. Therefore, an electrochemical equilibrium is established. When you say an equilibrium is established, what does it really mean? It means that the chemical potential of hydrogen is equal to 2 times the chemical potential of proton plus 2 times the chemical potential of electrons. That's what establishing chemical equilibrium means. Right now, we will not go into the expression that we are going to use for the representing the chemical potentials. All we are emphasizing is chemical equilibrium means this relationship is valid. The chemical potential of H2 is well defined if you can maintain the activity of hydrogen. Okay, this is from your chemical thermodynamics classes. You must have known that. Again, the chemical potential of proton is well defined if the activity of proton is well defined. So if I control the activity of H2 and if I control the activity of proton in the solution, I have a control over this and this quantity. Because I have a control over this quantity, what do I mean by control? I can reproducibly generate this quantity, and because this relationship is valid, I can reproducibly generate the chemical potential of electron. That is, I have a bath of electrons at a specific energy level. Okay. Once I establish the activity of H2 and proton in this system. So it gives me a reference value for electrons and for the energy of the electrons. So just to emphasize, controlling the chemical environment in the standard hydrogen electrode gives me a control over the electrochemical potential of electron in the standard hydrogen electrode. Electrons are in the platinum metal. Why do I use platinum? As I mentioned, platinum is a good electrocatalyst. It being a noble metal, it is impure and its surface can be reproduced easily. That is, the surface means, in this case, the interface I'm discussing is the interface between platinum and the electrolyte. It can be, it is not contaminated because platinum is a good noble metal. So on one side of the voltmeter is a lead that is connected to the standard hydrogen electrode. So what does a voltmeter measure? It measures the difference between the chemical potential of two electrodes. An electrode is a constant energy bath, okay, under open circuit condition or at an equilibrium. So on one side, I have the energy of these electrons, which are established by this chemical equilibrium. So let's understand. So I have established the energy of electrons here. Using such an energy level, I can measure the energy level of electron present in any other electrode. Okay, so that is the advantage of utilizing an reference electrode. However, this standard hydrogen electrode, even though it is very fundamental, it is hard to reproduce in most laboratories. It involves gases and other not easily implementable experimental solution. So few other reference electrodes are commonly utilized. The most popular electrode is the silver chloride electrode. So silver chloride electrode. How do you utilize this reference electrode? Again, this silver chloride electrode provides a reference energy level. How is that reference energy level established? It is established by another chemical equilibrium of relevance to this interface. In this interface, there is a this chemical equilibrium is established. Because of the existence of such a chemical equilibrium, I can relate the chemical potential of the electrons, these electrons are present in this electrode, to the chemical potentials of these three quantities. So when I use this reference electrode, I have electrons at this chemical potential, I can measure that energy level against the electrons that are available from a standard hydrogen electrode. This measurement has to be made experimentally. Even though I can interpret all these things using chemical thermodynamics, note that you have to make these measurements empirically. Unless you make these measurements empirically, I can't get out a number in this system. This is a very popular electrode. Before this, there was a popular reference electrode, which is also implementable, called the calomel electrode. Corresponding to this calomel electrode, there's a different chemical equilibrium, and hence electrons available at different chemical potential. Okay. Corresponding to each chemical potential, when I make a measurement via a voltmeter, I will get a different voltage. This is being gradually replaced because of the poisonous nature of mercury. Because of mercury pollution, standard calomel electrode is replaced by silver chloride reference electrode. You should note that these are not zero. Obviously, there exists a difference between the electrons in this bath and electrons that are present in this bath. All right. So let's get back to the question. So I had started with this copper zinc system. Let's take a copper electrode. When I have a copper electrode, let us make an experimental measurement against a reference electrode. Because the silver chloride electrode is calibrated against the standard hydrogen electrode, even though I'm using this experimental setup, I can relate this experiment to this chemical reaction. In this chemical reaction, this, and this are connected to the quantities that are relevant to standard hydrogen electrode. Okay, let's understand two steps. The first step is I'm trying to analyze how this electrode is related to this electrode. The electrode potentials are related. Because this calibrated against the standard hydrogen electrode, in effect, I can relate the electrode potential of this system to the standard hydrogen electrode. When I am looking at this chemical reaction, I am involved in discussing the chemical thermodynamics of the system. So I write the relevant free energy change in the following manner. Before we discuss any further, I want to again remind you that the potential difference in any of these electrochemical systems can be connected to the free energy changes via this equation. All right. So the next step here is I am going to use the conventions that you must have learned in your chemical thermodynamics class to simplify this equation. What are the conventions that we are discussing here? This is the free energy, standard free energy, the free energy of pure metal, right? So this is 0. Another convention is that this quantity, the standard free energy of proton, is the same as the standard free energy of water. Okay, there is a deep reason connected to why these two cannot be independently measured. Okay, because of that, we use that convention that this and this are one and the same. Again, this is a standard quantity. This is also 0. All these things you must have known from your chemical thermodynamics class. So when you are measuring or computing delta G, the only relevant quantity here is the free energy of Cu2 plus. Putting this and this relationship together, I can say that En is represented by this equation. So let's understand what this equation is. En is the measurement that I make when Cu2 plus is in non-standard condition. Okay. To understand what is a non-standard condition, we have to define what is standard condition. Standard condition is when Cu2 plus is at unit activity. When Cu2 plus at unit activity, my En would be 0. And when you make such a measurement against your reference electrode, you will still get a value. Okay, that value is an experimentally obtained quantity. It can be interpreted using chemical thermodynamics, but you have to make a measurement against a reference electrode. That is important to know. So when you have a copper and Cu2 plus at unit activity, when I make a measurement against a standard hydrogen electrode, I will get a quantity E0, which has this value. Okay, and and when I measure it against this particular reference electrode, I'll get a slightly different value. Okay, what is important to note is this is the standard electrode potential corresponding to this reaction that is obtained by an experimental measurement. Okay, even though it can be interpreted in terms of chemical thermodynamics, I have to make an experimental measurement to get this number. Many such values are tabulated in your electrochemical potential tables that you will see in Wikipedia links or in any textbook of electrochemistry, electrochemical engineering will have this. We have to notice certain things. Let's just notice first, this is the copper electrochemical potential that we discussed in the previous slide, that is plus 0.34. Where do you establish 0? 0 is established for the standard hydrogen electrode. What is the reduction reaction involved in standard hydrogen electrode? 2 protons are added to 2 electrons, that is in equilibrium with H2. I'm measuring the electrochemical potential of all these systems against this reference electrode. Okay, so this is, you can give the value to be 0. And then I'm measuring the value of standard potential. What makes it the standard? The activity of these species, right? Makes it the standard potentials. So let us look at the numbers and interpret and see whether it is consistent with our chemical intuition. Okay, so here I'm saying that electrochemical tables is based on thermodynamics and the thermodynamics is quantified by this equation, right? So we have the notion that lithium ion here is hard to reduce ion, right? Because lithium is alkali metal ion. It will always want to be as a monovalent cation. When I add an electron, it would be an endothermic reaction, right? So this is a negative number that I got out of measurement. When I multiply by here n equals to 1 and Faraday constant, I will get a positive delta G. Why is it positive? That is because it is an endothermic reaction. The act of adding electrons to Li plus is an endothermic, will give you an endothermic reaction. On the other side, you have fairly electronegative elements, fluorine, oxygen, chlorine, and so on, silver, copper, silver, gold. These are all in the same period, they are all electronegative elements. So silver means by silver plus, I mean. Okay, so when I add fluorine to fluorine, if I add 2 electrons, fluorine has sufficient electron affinity. That means this reaction is an exothermic reaction. this is a positive quantity. When I implement this equation, I will get a negative quantity, meaning that this reaction is an exothermic reaction. So our numbers that you get that are tabulated in electrochemical tables are consistent with our notion of that is born from chemistry, which of the element will want to be in a positive oxidation state. Like, for example, lithium, sodium, potassium, rubidium, cesium, all these things are alkali metals, right? Will have negative standard potentials. Okay, so these are alkali earth metal that also has a negative standard potential. That means the delta G of this reaction, adding electrons to Mg2 plus, is exothermic. And then there are two other things that I've mentioned: oxidizing agent and a reducing agent. What is an oxidizing agent? Oxidizing agent is that which oxidizes something, and while it oxidizes something, it itself gets reduced. Supposing we use, let's say, fluorine as an oxidizing agent. When fluorine is used as an oxidizing agent, during that act of oxidizing, it will get reduced. Okay, so the oxidizing agent, the ability to act as an oxidizing agent increases in this direction because the tendency to get reduced increases in this direction. The opposite is true for reducing agent. Okay, so a reducing agent is one that would tend to will get oxidized, right? So here these will tend to get oxidized more. So these are as you go from top to bottom, you have reducing agents of increasing strength. The last thing I want to emphasize is, in the conventional electrochemical literature, it is emphasized that what is mentioned in the table is a reduction potential. Okay, so reduction potential is also associated with oxidizing agent, right? When an oxidizing agent acts, it tends to get reduced. When you have a greater positive number, that means it is a better oxidizing agent because its tendency to get reduced is greater. Okay, so all these are related notions. When you say oxidation, reduction, okay, you can define it in terms of increase in oxidation number or transfer of electrons. When you add an electron, you are reducing that chemical species. Okay, it's also defined in terms of oxygen and hydrogen exchange, but that is not something which we are discussing here, because we are mostly concerned with electrochemical systems. But having said that, those definitions of oxidation and reaction based on oxygen and hydrogen is also consistent with these definitions. Okay, but we won't be discussing that any further in this lecture, but we'll take it up probably in a later lecture. So you have to have a good feel for interpreting this table that's going to be used often in all your electrochemical systems. The last point which I want to discuss is a subtle point. Let us go through this carefully. So what is the system we are looking at? We are looking at an electrochemical interface. What is the interface? Let's say you have a copper metal dipped into an aqueous system. When we represented E0 for that system, Cu2 plus was at a particular unit activity. Okay, so let's not even consider that such a system. Let's consider even a simple system, in a simpler system, copper rod being dipped into an aqueous solution. When that happens, little bit of copper will dissolve into the solution till the point chemical equilibrium is established. This particular chemical equilibrium will be established. When copper dissolves as Cu2 plus into the solution, the electrons that are generated gets accumulated into the copper rod. Because the chemical equilibrium is established, there is no longer any further net charge transfer, and you can write this equation. This is the stoichiometric coefficient involved in this reaction. This is the chemical potential. So what I want to do is that I want to introduce this new term called electrochemical potential, and using that we will also elaborate another point. The electrochemical potential of Cu2 plus has two parts. There is a chemical component which is represented using this equation, and there is an electrical component. This chemical component will depend upon the chemical properties, chemical bonding properties, solvation energy, and so on. This electrical component predominantly depends upon the charge state of Cu2 plus. The charge state is 2 plus, and this charge state, this charge ion, is present in a solution having a particular Galvani potential. Okay, so that's the way we define. So how is this potential generated? Initially, the solution was neutral. I dipped a copper rod. When I dipped a copper rod, copper 2 plus were generated. And because that copper 2 plus was generated, there was neutrality in the solution was broken, and it gave rise to generation of a Galvani potential. Okay, so based on the Galvani potential present in the solution, I can define this quantity. This is 2 plus Faraday's constant, and this is the Galvani potential. So once I have this definition of electrochemical potential for Cu2 plus, I can utilize such a definition and write down this equation in detail. So I'm writing this equation here. Because the chemical equilibrium is established, this is 0, and the sum of chemical potentials is 0. Right? So I'm going to utilize these expressions to elaborate on this. Cu2 plus depends upon these two quantities. This is the Galvani potential. This is the activity of Cu2 plus in the solution. A metal is a neutral quantity. It's in zero oxidation state. And by definition, the activity of a pure metal is 0, right? The activity is 1, therefore ln activity is 0. Therefore, mu Cu is just mu naught Cu. And then the electrochemical potential of the electron is written in the following manner. This is the potential that is present in the metal electrode. Remember, when copper got dissolved as Cu2 plus, it resulted in the generation of a electrical potential in the metal. I'm just implementing the charge here into this equation. Again, by convention, the activity of metal, of electrons in a metal is taken to be 1. Therefore, this quantity will be 0. Therefore, electrochemical potential of electron is this quantity minus F times phi m. Putting all these three equations into this equation, I get this quantity. What is this quantity? This is the difference between the electrical potential or electrochemical potential present in the metal minus the electrochemical potential of the solution. These two go by different names. This goes as the Galvani or inner potential. This potential difference, where does this potential difference reside? This potential difference resides at the electrode-electrolyte interface. This potential difference can be interpreted using this chemical thermodynamic relationship. All I've done is just substituted these relationship, okay, and put together. Even though we can interpret this potential difference using all these terms, I cannot make an absolute measurement of this potential difference, okay? So the measurement I can make is only against another reference system. The reference system I will be interested in is the reference electrodes, okay? So the reference electrodes can be like the standard hydrogen electrode, calomel electrode, or AgCl electrode, okay? So when I measure against that reference system, I will get the electrochemical potential difference, which is the potential difference between the chemical potential of electrons present in your system against the chemical potential of electrons present in the standard hydrogen electrode. Okay, so we have tried to discuss a lot of subtle points in this lecture. I'm sure there will be a lot of questions. We'll take it up in the discussion hour. So in the next lecture, we will look at electrochemical set potentials that have more complex junctions, like liquid junctions and so on. And we'll also utilize all these notions into a very useful quantity called the four-way diagram, which is very important for understanding corrosion, batteries, and so on. Okay, so we will look at that in the next lecture. Thank you.